One of the most frequently asked questions about the origin of the universe is, where did the Big Bang happen? Perhaps some of you also have this question. In this video, we'd like to try to explain how things really are. Can we say that the Big Bang happened at a specific point? And if so, can we say where it is? Can we identify it? Let's try to understand this. The first thing to understand is where the question comes from. Why do many people wonder where the Big Bang happened? The reason lies in the way the origin of the universe and its subsequent evolution are often explained and described. In the mental image that many people construct from this description, it is often said, for example, that at the beginning, the universe was tiny, concentrated into a pinpoint, occupying a dimension much smaller than an atom. Or it is said that everything started from a gigantic explosion, the Big Bang. However, this way of describing things is somewhat imprecise. It's fine when explained in a popular science context, but it leaves doubts and creates confusion. So, let's try to better understand how things are. First of all, the Big Bang is not an explosion, or at least not an explosion in the conventional sense of the term. When we think of an explosion, we think of something that happens at a specific point in space and scatters fragments all around in every direction. Think, for example, of the explosion of a supernova. The explosion happens at a certain point in space, and from there, a cloud of material expands all around, occupying more space. If we are at another point in space, we can see the explosion and say that it happened at that point, locating the source of the explosion. In this case, it makes perfect sense to ask where the explosion occurred. What the point is where the supernova exploded. When people ask where the Big Bang happened, they do so because they imagine the Big Bang to be something like this. Something that happened at a point in space, and from that point, matter was flung around at great speed, and the universe began its expansion. Moreover, it is thought that the expansion of the universe is precisely this matter moving away from the central point where the explosion would have started. But in reality, the origin of the universe and the expansion of the universe have absolutely nothing to do with such an image. This is not what we observe. What we have known for over a century now is that, if we look in every direction, we see distant galaxies moving away from us according to a precise law, called Hubble's law, which tells us that the speed at which these galaxies are receding increases with their distance from us. So, the farther away galaxies are, the faster they are moving away from us, but all of them are moving away. This motion of the galaxies might superficially suggest a great explosion that scattered these fragments, in this case, the galaxies, far out into space. But in reality, this is not the correct interpretation. According to Einstein's theory of general relativity and the Big Bang model derived from this theory, the motion of the galaxies does not come from something having flung them in all directions from a central point, but is due to the expansion of space itself. In reality, the galaxies are not even moving in space. It is space that, expanding, makes them move away from each other. This expansion does not occur within space because the universe, by definition, is everything that exists. The universe is not contained within something else. If it were contained within something else, that something else would also be the universe. The universe contains everything, so it is all of space that is expanding and not occupying other space where there was nothing before. We know, it's hard to visualize, but that's how it is. Moreover, the expansion has no center. Space dilates everywhere in exactly the same way. Indeed, at any other location in the universe, we would see galaxies moving away just as they do relative to ours, following Hubble's law. So, any point in space can be considered, in a certain sense, the center of the expansion. There is no special point where things happen differently. This fact, that the universe appears, on average, the same in any direction, is something we have verified with observations. When we observe the distribution of matter in the universe on the largest scales we can observe, we do not find any point where the density is much greater, as would happen if that point were the center of a traditional explosion. On the contrary, the universe appears uniform in every direction. There is also another important observation. When we look far into space, we are also looking back in time because we are receiving light that has been traveling for increasingly remote periods. So, in practice, we are rewinding the history of the universe and looking closer and closer to the time of the beginning of the expansion. Well, looking farther and farther away, we do see that the density and temperature are increasing, and this is true in every direction. Going back in time, at some point, we encounter the cosmic microwave background radiation, which, according to the Big Bang model, is the direct evidence of the initial phase in which the universe had extraordinarily high density and temperature. This is really important, so it is worth understanding well. If we look in a certain direction, photons reach us that started about 14 billion years ago when the entire universe was as hot as a star. If we look in a completely different direction, photons that started from the same epoch but from a completely different region also reach us, and those photons have exactly the same characteristics. This means that the entire universe, about 14 billion years ago, was indeed in the same state. The Big Bang happened both here and there, in whatever direction we look. We continue to receive the trace of that initial phase. In reality, we can say that the Big Bang happened everywhere in exactly the same way, including the point we occupy right now. About 14 billion years ago, all of space contained matter of extremely high density and high temperature, and this is the phase we conventionally call the Big Bang. Okay, but if the universe was much denser in the past, does that also mean that all the matter was concentrated in a smaller volume? So, can we say, as is often said, that everything sprang from a tiny dot of very dense matter? This is also not entirely correct because we do not really know if the universe is finite or infinite. What we can say is that the region we can observe is finite. Why? Well, because light has only had about 14 billion years to travel, so we cannot look any further. Anyway, the universe has a horizon, a limit beyond which we cannot make observations. But this does not mean there is nothing beyond that limit. This region, the observable region, going back in time, was indeed smaller. Approaching the Big Bang, from any point, the region of the universe you could have observed was much smaller than what we can observe today. But we do not know if the universe continues indefinitely beyond the horizon. In fact, based on observations, there are good reasons to think that the universe is incredibly larger beyond the horizon. Hypothetically, it might even be infinite. So, the fact that the density at any point in space in the past was enormous does not necessarily mean that the volume of the entire universe was smaller. Infinity, even if you compress it, remains infinite. It is more accurate to say that at every point in space, the density was much greater in the past, and the region of the universe that could have been observed from that point in space was indeed tiny. But this, once again, applies to any point in space. Thanks for watching. If you liked the video, please leave a like, subscribe to the channel, and turn on the notification bell so you don't miss the next videos.